When you're underwater and you're swimming around all happy, you and other objects underwater feel lighter. It's easier to lift things. You can bounce around and you can jump higher. But when you push through the surface of the water, suddenly everything is heavier again. This is an example of buoyancy. It's easier underwater because the water is pushing you up. Another example of buoyancy is a lot of objects can float, like rubber ducks, wood, leaves, and these float because there's enough buoyancy to keep them from going underwater at all. So buoyancy looks something like this. Say you're swimming here, gravity is pulling you down, but to balance that, buoyancy pushes you up, and this force is called the buoyant force. Where does this come from? Why does this force exist? It happens because the deeper you go, the more pressure there is, right? Let's look at a diagram. Imagine this is some random fluid. You have a bowl. The deeper you go, the more pressure, because pressure in fluids is dependent on depth. And since pressure is exerted in all directions when it comes to fluids, then that means there's a pressure pushing this bowl down, and there's also a pressure pushing it up. And the pressure at the top is less than the pressure at the bottom, because the pressure at the bottom is deeper, more depth, more pressure. So this is stronger. And what happens when this force pushing us up is stronger than the one keeping us down? We start to rise. Let me show you where the buoyant force equation comes from and what it is. Let's say this down force is force 1 and this force pushing us up is force 2. Then the buoyant force would be the total vertical force going on here. And that would be how much we rise. So that would be the difference between F2 and F1. From the pressure equation, which is force over area, we can rearrange this for force and get force equals pressure times area. This means that each of these forces can be written as PA. So P times A. But remember, pressure is also equal to density, gravity, height when there's depth and fluids involved. So this becomes density, gravity, height, aka pressure, multiplied by area, minus the same thing for the first force, PGH times A. And remember, this is area squared, since we're talking about pressure. Everything here is actually all the same. So this is density of the fluid times gravity times A times the change in height, because height is changing. Area times height is equal to volume. So this gives us PF times V times G. But we can go one step further. Density times volume is mass. Why? Because the density formula is mass over volume. And we can rearrange for mass to get mass equals PV. So the final equation for buoyant force is this right here. And this one right here is also a variation. You see both of these. What does this mean? This is Archimedes' principle. Archimedes was a genius from ancient Greece. And what this equation tells us is that the buoyant force on an object equals the weight of the fluid displaced by the object. So imagine a bathtub, and it's got a certain amount of water in it. When you hop in the bathtub, the water rises. That's the fluid displacement. The amount of water that had to rise to compensate for you sitting in the water. And the weight of this amount of fluid is equal to the buoyant force. Archimedes' principle is valid regardless of the shape of the object. This example is fun. Imagine 2 tubs of water. They're the same size and they're both filled to the brim with water. But the second one has a wooden block floating in it. Which one weighs more? According to Archimedes' principle, they actually both weigh the same. The amount of water that the wood displaces is the same weight as the wood. This is a quick example problem now. Imagine the ocean, and down on the ocean floor, buried in the sand, is a treasure chest. This treasure chest has a mass of 55 kilos, a volume of 0.024 meters cubed. What is the force to lift this upward at a constant rate? So, no acceleration. The force required to lift this upward has to be more than its weight. But there's also some other things that come into play here. since we're underwater. Let's solve this. The weight is equal to mg, which is 539 newtons. So that's the weight. The buoyant force. Remember there's two formulas, and these are on the free cheat sheet in the description. But the buoyant force formula we'll use is density, volume, gravity. The density of seawater, because it's salty, it's actually a little higher than freshwater. The volume is this, and gravity is 9.8. The answer for the buoyant force, when you plug in your values, is 241 newtons. So that's the amount that the buoyant force is pushing up. Now all that's left is to find how much force we need to lift it up. So the weight is 539, and this is the reason why things are lighter underwater, because the buoyant force is supporting it. So we can subtract 241. That means anything over 298 newtons will lift this chest if it's underwater. You don't have to put in 539 newtons of force because the buoyant force is helping you. But when you do lift your chest out of the water, you're going to need the full 539 newtons of force to lift it at all. You feel the full 55 kilos of mass. The key here is that depth is irrelevant for the buoyant force. Depth affects pressure, but the buoyant force, it does not care how deep you are. The buoyant force is the same. This is one of my favorite stories from history. And Archimedes with his genius megamind was sitting in his bath, trying to figure out a request from the king. The king got a new crown, and Archimedes was tasked to find out if this crown was gold, or if it was a mix of different metals, or just a complete fake. And this is the problem we're going to solve. So let's set up the problem. When the crown is in the air, the mass is 16.5 kilos. When the crown is underwater, the crown weighs, apparently, 15 kilos. Is it really gold? And the way we're going to find out if it's actually gold is that gold has a very specific density of 19,300 kilogram times cube meters. And if our crown matches this density, then it's gold. Anything less, it's a fake. So your crown out of water, like we said, 16.5. When it's in water, it's 15 kilos. Which means that the buoyant force is 1.5 kilos worth of force. And of course, you would write that in newtons because it's a force, but we're going to ignore that. We got 1.5 from the difference in weight. When it's underwater, it weighs less because the buoyant force is pushing up with this much. 1.5. The buoyant force, if you remember Archimedes' principle, is also equal to the weight of the water displaced. So the amount that the water rises when we're in our tub is 1.5 kilos of water. Now, our goal is to find density. The buoyant force, as we found, was how much it weighed outside of water minus how much it weighed in water. The difference. Now, what's special here is something called specific gravity. This is on the cheat sheet as well. It's a comparison tool. It tells you whether or not something will float. Tells you how dense it is compared to water. Specific gravity is found with the density of your object, aka our crown, divided by the density of our fluid, which is water. Our next step is to find equations for these density values. So let's begin with the density of the object, which is our crown. There's an equation that includes density, which is mass equals density of the object plus volume times gravity. Solve for density by dividing by Vg, you get density equals mass divided by Vg. For density of the fluid, what equation has fluid density in it? The buoyant force equation, it looks like this, has fluid density. So do the same thing as you did up here, divide by Vg. And you get Pf isolated. So the density of the fluid is the buoyant force divided by Vg. How do I know this? Get the cheat sheet. Let's go back and plug these into our fraction. And it would look something like this. Density of the object divided by density of the fluid. We can cancel these Vg's to get m over buoyant force. From here, we can expand buoyant force into this, which is mass minus the mass underwater. And we know these values. Mass is equal 16.5, and the difference in mass is 1.5. So here's our new equation. Density of the fluid we can actually write as 1000. And that's the density of water. And now we can isolate object density by multiplying both sides by 1000 to cancel it. And the answer is 11,000 kilograms per meter squared. This is not the density of gold. Gold density is 19,300. So our crown is a fake. To sum it up, here's what we did. We identified what we were looking for. So we're looking for density of our crown so that we can compare it to the density of gold. And then we found formulas that linked everything together. Really, that's most physics problems. And all this rearranging, make sure your math is strong so that you don't make mistakes. How do things float? Why would something float? If the object's density is smaller than the density of the fluid, then it will float. If the object is more dense than the fluid, then it will sink. And what if the object is on the surface of the water? So some of it is submerged, the other half is not. How does this affect the buoyant force? Say you had a bowl and it's floating in the water, it's 50% submerged. This water has a depth of h. When this bowl is put into the water and 50% is submerged, then the water will be displaced by 50% of the bowl, because the water is going to rise a little bit. So the height will increase. And when the bowl is fully submerged in the water, so 100% of it, then the depth of the water increases by 100% of the bowl. So the more it's submerged, the more the water will rise. AKA the more mass that gets displaced, AKA the buoyant force. This is pretty straightforward. The more the object is submerged in water, the more buoyant force is active until it's completely underwater. Imagine a ball with a specific gravity of 0.6. So that means it's 60% dense as water. The volume of this ball is 0.5, and the mass can be found with the formula density times volume, which is 0.6 times 1000, which is the density, times 0.5, which is the volume. This is a 300 kilo bowl. If the entire bowl is submerged underwater, then the water it displaces is half a cubic meter, since that's how much space it takes up. Half a meter cubed of water is equal to 500 kilos of water, since 1 meter cubed is 1,000 kilos. That means the buoyant force acting on the bowl when it's fully submerged is worth 500 kilos. But the bowl only weighs 300 kilos. So what happens? It starts to rise. The bowl will then rise and rise until just enough of it is underwater to displace 300 kilos of water. And then it's in a state of equilibrium. It's floating perfectly. The buoyant force and gravity perfectly cancel out. 300 kilos of displaced water means that 0.3 meters cubed of water is being displaced. Since the bowl is 0.5 meters cubed, and only 0.3 meters cubed has to be underwater, then that means 60% of it stays submerged for it to float. This is probably the favorite example I've ever done on this channel. And before we start, here's how you should think about air. Air is literally just water but less dense. Of course, it's still a fluid, but it's just less dense. It's just thin water, and water is just heavy air. So here's the problem. Have you watched the movie Up? In that movie, they have a house, and this house, the old man doesn't want to move, even though everyone's trying to buy his house. So they tie a bunch of balloons to it, like 1,000 something balloons, and it starts flying up. How much volume of helium did he need to lift this house up? So to make this simpler, we imagine like this, the house and one big collective bunch of helium. So one giant balloon, you can imagine it as. It would do effectively the same thing. and we're looking for the volume of helium needed. To start, let me tell you, the density of air is 1.29. The density of helium is 0.18. And by the way, that's why helium makes things float, because it's less dense than air. And because air is basically just water, you can look at it like water. Like things can float. Like it's got pressure and everything. It's a fluid. That means there's buoyant force present in air. It's just never enough to make things float. That's why people aren't flying around. Let's say this house is really tiny. The mass of the house is only 1,200 kilos. And how do we solve this problem? What are we looking for? We're looking for how much helium volume is needed to make the buoyant force of this house lift it up. So what we're saying in equation terms is the buoyant force must equal the weight of the house, at least. That's the minimum. The buoyant force is found with the density of the fluid, which in this case is air, multiplied by volume and gravity. And the mass of this total system would be the mass of the house plus the mass of the helium balloon. This volume represents the helium inside the balloon. And this is multiplied by gravity as well. But we can cancel that out. So that's the equation we're left with. I just went and wrote our equation up here, so it's a bit easier to read. We're now ready to solve for volume. We do this by putting both of the volumes on the same side. So, he air V minus P he V equals 1,200. We can divide both of these one by one. You get V equals 1,200 over air density minus helium density. And guess what? We know both of them. The answer is roughly 1,081 meters cubed of helium. How big would this balloon have to be? To have this much helium would need to be roughly 13 meters wide. But this is when the buoyant force is equal to gravity. So if we wanted to actually fly and lift off the ground, we're going to need more than this. Anything more than this will start flying. This makes studying 10 times easier. Go download the free cheat sheet in the description, and I'll include a free surprise worksheet from my premium study kit to help you understand this topic.